Good afternoon. So, we are on a journey of trying to obtain in some rigorous, reasonably systematic fashion, right? The white noise limit of an ODE that is being driven by a fluctuating process which is colored, because only then it's an ODE. Right? So, if I take a normal dynamical system and I add a forcing term, which could be stochastic, but it's some colored noise. That means it has a finite correlation time. In other words, it's some smooth signal. It's random in the sense that each time I generate that signal, somehow I will get a different kind of signal, right, which is fluctuating. But it's smooth in time. So if I zoom in enough, it is differentiable. Then I can always, for each such realization, solve an ODE. Then I can look at statistics, etc. But I don't need special mathematics. I only need something special when I take the white noise limit. That means when I make that correlation time vanish. Okay? And we want to find that limit. And then I said to be able to go there, we have to use certain mathematical techniques, which ultimately come from the idea of center manifolds and slow manifold reduction. That's why we decided to first look at this and then come back and bring those tools to our stochastic problem. Okay. So in the last class, we looked at what is a slow manifold, right, in a simple dynamical system, finite dimensional setting. And we saw that basically if you have a dissipative system with many fast processes, and maybe one or and a fewer slower processes, right? The fast dynamics will collapse, and then the long time slow evolution will happen on some subspace where all those fast degrees of freedom are not zero, but their values are more or less completely determined by only the slow variables. So it's like a quasi-static sort of situation. Right? They're not fixed in time, but the values of the fast things are always somehow being determined by only the slow variables. Okay, so I can therefore determine how the system is going to evolve in long times just by calculating the values of the slow variables. Okay. But usually the evolution of the slow variables also involves the fast variables. So you need to find the expression of this manifold, which basically tells you how the fast variables, what are the values of fast variables given the slow. Right? It's like specifying a surface in this hyperspace. If you know this, you can plug in this expression for the fast variables in the equations of the slow, and then you'll get a closed system. Right? This is the reduced model. So the challenge is to get the expression for this slow manifold. Okay. So we saw how to do it in the last class in the simple ODE example, right, which I showed you from that paper. Today we are going to apply it to a PDE problem, which will bring us closer to what we want to do later. Okay. And it's also a classic problem, which is instructive and interesting in its own right, again from transport, which is that of Taylor-Aris dispersion. Okay, so here I am showing you a simulation in a 2D channel flow. Okay, I have a fully developed laminar Poiseuille flow in the background. Okay, so you can think of it as flow between two flat plates, right, which has a parabolic velocity profile. Okay. The parabolic velocity profile is important. Now, into this flow, I put in a dye, a slice of some color, right, which you can see. Right, this is the blue dye. So on top, I am showing you the dye itself. So this is the y coordinate, which is the transverse direction. These are bottom plate, top plate, right, transverse direction. Nothing is changing out of the plane. And then in this x direction, you have flow. Okay. And what I do is, and it's a parabolic flow, so the velocity is 0 at the walls and maximum in the middle. I then put this slice of dye. Okay. Now what you'd expect to happen is, immediately the velocity profile should distort this slice, because the center of the slice will move faster than the stuff near the walls, which in principle should not move. Now, of course, this is some diffusing species, so there will be some diffusion, which will further distort the shape. And so we'll see how that evolves. Now, what is of interest is, if you want to know the details, you have to just solve the equation, as I have done here, and I will show you. Yet the question of trying to do some reduced model comes when you are saying, okay, at long times, I'm interested not really in the full distribution across the channel. I just want to know what is the average concentration at different times, right? Or if I'm standing at the outlet of this channel and I'm looking at this dye being released, I want to know what is the release profile, okay, the average release profile. So I don't care how it varies across the channel, I just want to know what is coming out as a function of time, okay. So one way of thinking about that is to just look at the concentration that is averaged across Y. This is the cross-section averaged concentration that is plotted below. Okay, so I'm calling it C bar here, and it's normalized by the max so that you can see the shape. Okay. And yeah, and so what initially I have given a thin slice. So this, it looks like a Dirac delta, some kind of spike. Of course, not exactly Dirac delta, but you can imagine it approaching a Dirac delta. The thinner I make it, the taller it must become for a given amount of input dye. Okay? So this is similar to the diffusion problem where you put a pulse and you watch what happens, except now here I have diffusion in the y direction, yes, but I also have this advection in the x direction with a parabolic profile, so it's more complicated. And what we will do is, as we see the concentration spreading on top, okay, you will also see how the cross-section average below modifies. So let me play that again from the beginning. Okay, so of course, if you pause it here, so what is happening is, as you expected, the center line velocity is higher, so it causes more transport along the center line, right? And the stuff near the walls is being left there. At the same time, diffusion is going to cause it to smear out a bit, right? If there was no diffusion, you would just get a parabola. It would be like tracers going with the flow, but of course there is diffusion. Okay? Or the tracers are undergoing Brownian motion, but I'm solving directly the diffusion equation. Okay? That's already a hint of why what we're going to do today's class connects to our white noise problem. Anyway, so moving on. Okay, so you can see that it keeps getting distorted, but somehow diffusion is also countering that distortion by making stuff near the wall come towards the center and vice versa. Now, while all of that is happening, if I just average across each slice, right, at every x I average across y, I get a value, I'm plotting that here. So if this is somehow you're zooming out far away so that you cannot see the y direction, it becomes one dimensional. You're only seeing the variations, effective variations along x. Those variations will look like what's happening below. So it's a zoomed out picture or a large scale picture, right? I'm not yet looked at large time because I'm still close to the initial, right? So it's time is being carefully monitored, right? Looking at it evolving, but you're zoomed out. And you can see it will have this kind of interesting shape, right? Some kind of complicated spreading is happening of the initial narrow pulse. And if you keep watching, now look at the bottom, you keep watching the pulse, right? It starts to smoothen out. And after some time, it remarkably looks Gaussian. So this is almost Gaussian now. It has some slight asymmetry, right? And then if you look on top also, things have become somehow much more symmetrized, right? Of course, by the effect of this diffusion. But diffusion is not in the x so much as diffusion happening in the y direction, right? The y is short. So of course, diffusion there is much faster than what it can do in the x direction. Okay, and now if you take long time scale picture, right, you will see it is Gaussian. So what I mean by long time scale, if I'm not interested in the details, small time, it would be like, okay, I have this initial profile and I'm looking at the phenomena evolving on long time scales. That means I would go from something in the beginning, directly jump to something like this 13 seconds. Right? So if I were to do that, I would say, oh, there's a pulse, right? I have a Dirac delta type of pulse, and at long times it's spreading like a Gaussian. And henceforth it will keep spreading like a Gaussian. Okay, so empirically, by looking at this experiment, simulation experiment, of course people did these experiments. Taylor in fact did many of these, he did the first experiments systematically to look at this phenomenon. What you would see on long time scales is that if I put a localized source, it spreads like a Gaussian sufficiently downstream at long space and time scales, and it keeps spreading like a Gaussian. And this looks like the solution of some 1D diffusion equation, because if I take just without any advection, or rather, I have a 1D equation, advection in x at some uniform speed, and diffusion in x, I would get this result, right? I would take a pulse, the pulse would move at some speed while it diffuses. It's like standard 1D advection diffusion. So the remarkable thing is you have got something like 1D advection diffusion from what is a 2D problem with advection which varies in the r direction. That is crucial. Otherwise, what would happen is, if you did not have this u as a function of r, what would you expect? If you just had plug flow, right? No cross-section variation, then my entire pulse would just keep moving. Okay, it would not get spread out. It would just move like a localized pulse. There will be no spreading. Some spreading will be there because of diffusion in the x direction, but this will be very small. Right? So obviously, if you look at the movie, the bulk of the spreading, it's clearly happening because of the advection, right? Especially at early times, you see the advection, the entire width is being dominated by the fact that the pulse is getting distorted out. So definitely, if you look at, and this we can of course do from the experiment itself, if you just look at this concentration profile, which is easy to do an experiment, you put a pulse, you stand at the outlet and you measure the concentration coming out, you will get a Gaussian profile at some distance. Right? You change the flow rate, that will be as good as decreasing the distance. Reduce the flow rate, that will be like going to a larger distance. Right? Or you can make pipes of different length. And you keep measuring this Gaussian, so you can see how the Gaussian spreads along the length, right, or in time. And you will find that the spreading of the Gaussian will, of course, give you some effective diffusion coefficient. This is orders of magnitude greater than the actual molecular diffusivity. So this is very easy for Taylor to see. So he knew it is not just this diffusion. It's somehow a mean effect, some kind of net long time effect of the advection that depends on r, that depends on the y direction. Somehow the dependence of advection, the velocity profile in y is giving you diffusion in x. Right? So first of all, the fact that directional advection should give you symmetric diffusion is itself strange. Okay? And that the variation in y should give you this diffusion in x. Okay? So this is a very interesting phenomena. Okay? So Taylor discovered this thing in some systematic way and gave a theory, a kind of intuitive theory. And Aris, who was a chemical engineer, right? Taylor-Aris, who is maybe more famous in reaction engineering circles for his chemical reactor book, Optimization Circles for Dynamic Programming. But he also did, in terms of fluid mechanics transport phenomena, he worked on this, which is also called Taylor-Aris dispersion. And in fact, his paper, which is published in the Royal Society journal, was sent to, I mean, at that time, a fellow had to communicate the paper to the journal, no matter who is the author. Right? So you have to, if you are an author, a young author, you have to send your paper to a fellow who will then, if he feels it's good, send it across. Right? So then the peer review is basically that initial phase. So Aris was quite young at this time. He was not yet a professor. He sent this to Taylor. And Taylor, of course, liked it. And so anyway, so it's a pair of nice papers. So in this, they analyze the phenomena. Since then, there have been more rigorous derivations. I will show you a modern version of this derivation. Okay, so what we're going to do in this class is basically, we will see that this effective dispersion is happening on the slow manifold. Okay. That in other words, whatever be the initial variation in y, that relaxes quickly because diffusion is very fast in y. So the rapid diffusion in y, if you wait on long time, so x is much longer than y, right? So if I look far downstream, the rapid diffusive mixing in y somehow gives you some averaged effect of the advection. Right? So the fact that the center line is faster, it's slower, that somehow averages out because of this rapid diffusion, so that on long time scales you get this axial diffusion type of effect, which we call axial dispersion. Okay? And underlying this is the fact that you're on a center manifold. That's why once it becomes Gaussian spreading, it is forever Gaussian spreading. It won't suddenly start being non-Gaussian, okay? Because you're sitting on that invariant slow manifold. But now the space is not some set of ODEs, right? It's a PD. The concentration field has infinite degrees of freedom. But from there, you will see that there is a one-dimensional manifold on which we can do our analysis. Okay? And what we do today will be almost directly relevant in an interesting way when we come back to our question of the white noise limit. Because there also you can see that when I say taking the white noise limit, I'm basically creating a separation of timescales between the noisy process and the process I actually am interested in, which is on the long timescales. So the same thing is happening here. We'll see in the limit of a very, very thin channel, we'll basically be saying that there is a process that transfers diffusion, which is much, much faster than the spread in the axial direction or the transport in the axial direction. And that timescale separation is what allows us to derive this reduced model. Okay, so we can now turn attention back to the board. Okay, and we are going to address this problem today. Okay, and we'll do it in a pipe. The simulation I showed you was on a channel, but it doesn't matter. The same phenomena will occurs in both cases, just some constants in the final equation are different. So if we look at the pipe case, it's a little more instructive. Okay, so what we have is a cylindrical pipe. This is the axis of symmetry, and the channel has a radius r. Okay, this is the x direction, and in general, I will have a concentration field, right, that evolves in r, x, and t. This is the radial direction, and this is the width of the channel, the radius of the channel, capital R. And now in this channel, I'm going to have a Hagen-Poiseuille fully developed laminar velocity profile. Okay, so which I'm sure you know how to derive. Right, from the Navier-Stokes, if we take fully developed unidirectional assumptions, right, you can get the velocity profile. I'm putting a star to denote dimensional quantities, which I will later non-dimensionalize. So u is only a function of the r direction. And one can easily show that it has the following relation. And this in turn you can write as twice the average velocity, 1 minus r square. Okay. Where the average velocity, so this is the cross section average. Okay. So this definition of the average I will use again and again, because remember we want to find an equation for how the cross section average is evolving. So it's basically you integrate over the radial direction, right? One second. 1 minus r square. So I'm putting the star everywhere because it's is dimensional, right? Okay, so the important thing is when I take the average, remember I have to include the volume element factor in cylindrical coordinates, right? So I have to have, it's not integral dr, it's integral r dr. Right? When you go from Cartesian to cylindrical, you have this Jacobian which accounts for the change in the volume element with r. That is important. And then you, to do an average properly, you have to also normalize it by the area, right, over which you're averaging. So that comes in here. Right? The 2 pi factor, of course, cancels out because we are going to assume things are axisymmetric. Okay, so throughout when I say cross-section average, I mean integrate the stuff with respect to r dr divided by integral r dr, which is the cross element, the cross-section area. This will just be, when after I scale things, it will be, if I scale the coordinates with capital R as I will do later, this just becomes 2. So it will be 2 times 0 to 1 r dr, okay, after we scale the radial direction with capital R. Anyway, so that is important. Okay, so now we have the setup. And what I want to do is start with the full PD for the concentration field, which in principle I can solve numerically as I showed you on the movie. But instead of doing that, we are going to try to simplify it to directly get an equation for the cross-section average, how it varies in x and time on long time scales. And this will be possible only if we satisfy certain conditions on the radius of the channel, as we'll see. Okay, so let's start with the equation first. Right, so we're going to take the species transport equation. Capital D now is going to be the molecular diffusivity. Okay. And I have diffusion in the radial and the axial direction, at least for now. Again, cylindrical coordinates, so I have the following expression. So it's 1 by dou r of r by dou r. Dimensional. Stars are dimensional for now. Everything has star. Okay, so this is just the standard advection diffusion equation in axisymmetric cylindrical coordinates. Okay, so now what we should do is the whole point in order to make progress, we need to somehow appeal to diffusion being fast in the radial direction, right, compared to transport and axial. So to make such statements, to find the right conditions, we need to scale the equations appropriately. Okay. So we have to choose scales. Now the scale of C doesn't matter, right? It will cancel out. It's linear in C. So we can non-dimensionalize it with something. We can use some C characteristic, it doesn't really matter, whatever it is. Okay. It could be, you could take it to be the initial, some kind of initial concentration, okay, depending off the pulse, for example. But anyway, so this doesn't matter. So we will write C as C star by some C characteristic, whatever it is. Similarly, we have to take U characteristic and so on. So the U characteristic, we will just take the average of the dimensional velocity. Okay. And the R characteristic should obviously be the radius. And the X characteristic is the length of the channel, length of the tube. Okay. Which we're going to say is much longer than R. And now we have a choice for the time characteristic, right? For now, let me take it to be L by R. We'll revisit that. Okay, so I'm generally going to be interested in anyway what's happening on long time scales. Okay, so this is like the long advection time scale. I could also have a short, sorry, I forgot a U, UC. L by, what am I doing? L by UC, sorry. Okay, L by UC, right? So this is a long time scale, right? Note that I could also have or R by UC, which would be short advection time scale. But I mean, that doesn't really make any sense because I'm anyway, the UC is in the L direction. So physically speaking, the only advective time scale is L by UC, right? There's no advection in R. What is happening in R is diffusion. So I could also have, so this I will not take, but I could also have a diffusion time scale. We should keep in mind that there is a diffusion time scale, which is what in terms of a diffusion coefficient? Right, R square by D. So D is meter square per second. So that will give me the time scale of the diffusion process, which I could have chosen as the time scale. Okay, but we'll keep that aside for now. That's the short time scale in the problem of the two physical processes, because you have diffusion in R, which is important. Right? You have advection in the X direction. These two are the main fundamental things. Right? And so the time scale of the R diff, which will be, you can already see now, is going to be small if R is small. Right? And similarly, the time scale of advection in X will be long if L is long. Right? So the thinner and longer the tube, the more will be the separation of time scales. And that's what we are interested in. Okay, so now if we use this scaling, right, that means I'm going to replace everywhere C is equal to, C star is equal to non-dimensional C times the characteristic C. Similarly, X star is going to be X non-dimensional into capital L and so on. Okay, so if you do this, then we'll get the scaled equations with some groups of parameters which will group into a non-dimensional group. So let's do that. Right, so if I take TC in that fashion, okay. So you get R square out from the denominator. The fact that this is an X square compensates, to compensate for that I have an R square by L square, right? And then I can of course move this to the other side. So I will get r square by d here. Okay, so I have only one group now, this group. Okay, and this group is, I'm going to call small p. It's like it's called the axial Peclet number. Okay, so UC of course is, I can choose whatever I've chosen it to be the average velocity. And this I could have also written as it is the same as this, right? So this RUC by D is what you can call it the radial Peclet number, right? The Peclet number is always a ratio of time scales of advection to diffusion, right? The relevant one for us is this R square UC by LD, because that is the ratio, if you see here, of the advection time to the, radial diffusion time to the axial advection time. Right? You can see this as a ratio of the two things. Right? It's a ratio of the diffusion time to the characteristic time which we have chosen to be the axial advection time, correct? So it's a ratio of time scales, and therefore it is going to be small if r is small relative to L, right, as you can clearly see here. In fact, if you write it in this intermediate way, this RUC by D is closer to order 1. Right? It's comparing advection in R to diffusion in R, but that's not really relevant. Right? What's relevant is the advection in the axial direction. Okay, but I've written it this way because sometimes people will call this the Peclet number, which is capital PE, radial Peclet. Right? What I'm interested in is that into the aspect ratio. Right? That can always be made as small as I like by making the tube long, just to point that out. So if you look at dispersion literature, you will see dispersion coefficients, which we will derive now, for a range of this number, which they will call capital PE. So for any value of this, my analysis is valid because I can choose L to be large enough, you see. So in fact, if you like, the value of this RUC by D, the radial Peclet number, will decide how long my tube needs to be for Taylor-Aris dispersion to emerge. Right? In other words, if, for example, if the diffusivity becomes smaller, right, then P will go up. To compensate, I need to take a longer tube. Okay, so in other words, if you take something that's diffusing very slowly, there will be quite a long development length before you get this Gaussian-like behavior. But if you say eventually I can wait long enough, right, then you will always get the Gaussian. The time horizon that you need to wait along the channel, right, is governed by this thing. Okay, so let's not worry about that now. We'll just look at small p. So when I do this, you will see that my equation will just be only small p is there in front of these terms. I'm also, just for simplicity, going to drop this r square by L square, which is obviously small. I don't have to drop it. If I keep it, everything that I'm going to do will also proceed almost without any problem. Right? But just to keep my amount of writing limited, I'll drop it. You can try to include it and see what happens. Okay, but it doesn't change the analysis. So I will drop r square by L square terms, right, which is basically the axial diffusion term, which is small basically compared to radial diffusion and compared to axial convection. So then after I do that, I will have the following equation. Okay, and of course I have to specify the boundary conditions. So that is just no flux at the wall, right, and symmetry at the center line. So that's what I've written in the corner. So now I'm going to write it in this operator form to connect it to what we did in the previous lecture. Right? So you see, in the end, I have a PDE, which is some infinite dimensional dynamical system. Right? So I have the left hand side, which has the time derivative plus this advection term, is equal to this linear operator acting on C. This linear operator is a differential operator, just a diffusion operator, right? 1 by R, etc. And it has those boundary conditions, right? And this is what is happening in the radial direction.
So isn't there a redundancy in the rotation? There are two capital L's.
There are two
Capital L's. One is the length of the tube.
Okay, yeah. So let's call it lambda. Thank you. Okay, so yes, to avoid confusion, the length we'll call lambda, and L is going to use L for the linear operator. If I was not writing on the board, I would use some bold capital sans serif font for L. Anyway, it's okay. So this is the state of the system now, fine? Now the point is what's going to happen as P goes to 0, because that's a physical limit of interest when we have rapid radial diffusion, slow axial advection, and we're looking at the system also on long time scales. That is, that would be mathematically saying looking at this problem as P goes to 0. Okay. So before we go there, you see that if P goes to 0, I'll lose the time derivative, which will make you uncomfortable because we are looking at a time evolving problem. Right? So that is true. So if I want to get a good physical sense of the problem as a dynamical system and connect it to what I discussed last time of center manifold theory, it's good first to just look at this problem rescaled. If I had taken Tc to be the diffusion time, okay, then you see that this ratio would have dropped out in front of dc dt, it will survive here. Okay, so if I had rescaled the problem like this, I would get the following. Let me write it the other way. Okay, I can always do that, it's just choice of time scale. So this would be looking at the system on the fast time scales. Okay, so on the fast time scale, diffusion is the dominant process and the advection, which is slow, is much weaker. Okay. If I decide to look at the problem, scale it on the long time scale, then you see these two of the same order. That means that time is capturing only the slow process, right? And this becomes much, much bigger. So if you want the proper way, better way of doing it is to do the bottom one, because it preserves a dynamical system nature, right? As Peckley goes to 0, you don't lose the time derivative. So this is, strictly speaking, better. But in what I'm going to do today, we will proceed with the thing on top simply because it is, in terms of doing the derivation, actually both are okay, but this is what Gardner does. Okay, so just so that you see the connection later on with the stochastic process thing in Gardner's book, we'll go back to the scaling on top. But whatever we're going to do, you can easily do with the scaling at the bottom. Okay. But this is good for us to see the following now, connected to what I was talking about center manifold. Okay. So you see this equation now. Now if I take P going to 0, what happens? I will get the following equation. Dou C by dou T is just equal to LC. So it's a dynamical system. You can think of L as a matrix. Okay. This is why it's nice to write it in this operator form. So it looks exactly like what I had shown you in the last class, right? You had dx dt is equal to some nonlinear f of x. If I try to linearize it about some fixed point to look at the dynamics, I can linearize it, I'll get a form like this, right? Except that I would have a matrix here. It's also a linear operator. This is a linear operator. I can get a matrix A if I simply discretize the R direction using your favorite method. Yes?
Isn't P1 when T is equal to T? Because P is
Sorry,
the
isn't?
ratio, P is the ratio of T.
Correct. P is 1. That's why it became 1 here, right? That is the point.
Yes, so how is P going to 0?
No, I am taking the limit of P going to 0. So I rescaled it, I changed so the equation after rescaling, right, makes the term in front of dc by dt 1. So I have a new equation. Okay. In this equation now, I want to take the limit of P going to 0. That means I want to take the case of a very, very long tube for a given radius, etc. Okay, so the point I'm making is that's to understand the character of this equation, right? In the limit of P going to 0, the equation simplifies to the following linear dynamical system. Okay. This L is a linear operator. Right? In fact, it will be a matrix if I discretize the PD in the radial direction. So the question to ask yourself, connected with what we saw in the previous lecture, right, is does this operator L have any zero eigenvalues? Okay, because if it does, then those directions basically will not evolve when P is 0. When P is non-zero, they will evolve slowly. So the slow direction on the system on which the slow manifold has to be constructed are again going to be related to the eigenvectors corresponding to zero eigenvalues of L. That is the kernel or the null space of L. Right? That's what I showed you in the last time. And that will be used to decompose the problem so that we can find the right coordinates, if you like, in which to construct the slow manifold. Okay, that is exactly what we did last time, remember? So in the previous lecture, we had x and y was fast, x was slow, but I said you don't always have this automatic decomposition. And then I showed you an example in a PD of how you can use that. Same thing is going to happen here. Okay? So to find the right coordinate to describe the slow manifold, I need to look at the null space of L, because that is the direction on which things are going to be slow. Okay. So the first question is, does L have this null space? If it doesn't, then there will be no basis to do this kind of center manifold reduction. Okay. So the question I would ask here is to look at the kernel, which is the null space of L. Right? That's like asking, is there some phi such that L phi is equal to 0 where phi is non-zero? Okay. Now, so now you look at the L. If I replace C by phi in that equation, so I'll have 1 by r d by dr of r d phi by dr equal to 0. Is there some value of phi for which that is true, which is not 0? Of course, if phi is equal to 0, it is 0. Right? But is there some non-zero phi for which you will get 0? Anyone? So you have a boundary value problem. You have to solve a boundary value problem. Right? Right, such that is a problem. So what phi is there some phi other than 0 that will satisfy this? Then that is the vector in the null space. Why don't you solve the equation? What is the problem? Just solve it, integrate it. Just integrate it a couple of times, no? The answer will be obvious. I think it's terribly obvious. Any constant phi is obviously going to satisfy it. Right? So this is true for phi equal any constant. Okay. So the phi being some constant is also a function. Right? It's a very simple function. Right? So any constant value of phi, right, is part of the null space. And the null space, of course, when you say spaces, it's a subspace, which means I need a basis in it, right, which I can then multiply by some constant. So the obvious basis would be just 1. Okay, so I can say that find the kernel of L, right, is just this spanned by this vector 1. So normalized. So, okay, so when I find the dynamical system of this linear form, and I want to look for, is there a slow manifold? I will look for whether the operator has a null space. We find it does, right, because of our no flux boundary conditions, etc. And that is just, the null space is spanned by 1. Right? By any constant vector, I choose 1. And that means if I multiply 1 with a constant, that's also in the null space. That's what we said. Okay. Now, having understood this, I can then come back and construct the center manifold the way I said last time. Right? So there are different ways of doing it. One way is to say, okay, now that I know this, I come back to the nonlinear problem. I project it using the null space. I decompose C into component on the null space and the stuff of the null space. In other words, the null space gives me the coordinate direction, and everything orthogonal to it is the fast stuff. Right? So I decompose my concentration in this way. Similarly, the equation also I project out in this way, and then I get a reduced equation. That's what we had done in the last class in the ODE problem, and then later with the PD quickly. That's what we'll do here. Okay, but before that, let me show you where even if we don't go this route, which is the proper center manifold way of thinking about it, I could see it purely algebraically from top. right? Which is why if you look at the literature, there will be many such, we call it homogenization, averaging, multi-scale method, where it's presented like an algebraic technique without the underlying explicit recognition that there is a center manifold on which dynamics collapse, etc., etc. Okay, but this is the correct dynamical way of thinking about it. The picture I showed you yesterday, right, that all the fast degrees of freedom are collapsing. That's why in long times I can try to get a simplified model, because the dynamics are happening on some low-dimensional subspace. Even though I'm in infinite dimensions, everything will collapse, so that in the r direction only one variable is important, which is the variable projected on the null space. So that is the reason of why it's going to work, right? Why our model will work. But just to derive it, you don't necessarily have to do this. Okay? Just purely as an algebraic way of derivation, you can skip this, right? And that's what you will find in Gardner's book and in many other places, right? But of course, implicitly in their mind, all this is there. So suppose I had done that, right? If I continue with this equation, if I continue with Tc equal to L by U, then I have this equation, right? Then if I take P going to 0, what I will find, right, it will be like saying I have this equation, I want to approximate C for small p. Okay, so just say, okay, let's the leading order approximation, or if I want, I can write C as C naught plus P times C1 plus P square C2. I try to do some power series, perturbation expansion, right? Whatever I have to do, I'll have to start by looking at the 0th order case. Right? So what is that if I put P equal to 0 here? What will I get? LC equal to 0, or LC not equal to 0, right? The 0th order behavior. And that will force me to say, oh, C naught is a constant. It's undetermined, right? I don't even know the leading order solution. So this tells me that a regular kind of perturbation technique will not work, right? So for those who are not familiar, when we say perturbation method, it's like we have some problem where there's a small parameter P, and I say, okay, I guess that my solution, if it has some smooth dependence on P, can be Taylor expanded around P. So I can write C as C naught plus P C1 and so on, P square C2, some power series. And then at least C naught will come out as a solution when I put P equal to 0. And if this had some value, good. I could then go back, get an equation by comparing powers of P for C1 and do this exercise. This is a standard regular perturbation. You can see here that standard technique will not work because I cannot determine it at this order. The value of this C naught is not known. That tells me I have to go to the next order. The physics that determine this C naught is not there when I take P equal to 0. So whatever I've thrown away is fundamentally important. I need to somehow account for it. Okay. So if you just look at it as an algebraic technique of perturbation method, then the Lyapunov-Schmidt method I talked about last time will immediately come into play. You'll recognize, oh, I have a null space of this leading order operator is a linear operator with a null space, so I cannot do regular perturbation theory. I need to do this Lyapunov-Schmidt type reduction where I project C onto the null space, and so then I will do exactly what I'm going to do now. Okay, so the point I'm trying to make again is, if you look at in what we will see in Gardner's book when we come to it, right, to the white noise limit, somehow this kind of problem will become relevant, and at that point we will see that okay, he will use this property of some linear operator. But underlying that in the back of our mind, we should say, oh, this is relevant, and I have to now project onto the null space of L precisely because that is the coordinate along the center manifold. So when I do it this way, if I put P equal to 0, I'll get this. And if I don't know center manifold theory, I will say I have to solve this equation. Whereas if you do this without knowing center manifold theory, you can just get this result and then carry on with some technique, which I'm going to do now. Right? It doesn't require you to know things about dynamical systems theory, eigenvalues, and manifolds, and so on. Right? So in a sense, this is direct, doesn't require you to understand dynamical systems, but you'll not know the answer of why the derivation will work. Here you know, because you recognize that, oh, this has a subspace where the dynamics are slow around the 0 eigenvalue. And then you construct this center manifold. Fine, but from now on, whatever I do, it's the same for both methods, more or less. Okay, so what we have realized now is I have this operator L, which is the diffusion operator, with these boundary conditions. That's very important. If, for example, I had Dirichlet conditions, it would not admit this 1 as being a solution. Right? So, for example, if I come here and instead of having the derivative equal to 0, I put phi equal to 0, then the only solution is phi equal to 0. So there is no null space. I mean, the null space is empty, which only has 0. There is no non-trivial null space vector. Then there are tricks to get around that, but at least directly the method will not work. Okay, so the no flux boundary conditions are important. Okay, so we know now that the kernel of L is just 1. So I will now proceed with the calculation I had shown in the last class, right? So step 1 is to decompose C, right? We'll decompose it into my new coordinate system, which is given by the slow direction, which is on the null space, and then off the null space. Right, so the stuff that is perpendicular, the complement to the kernel of L. Right, so I'm going to split it in that way. So that will be like saying C is equal to okay, so how do I get the part of C which is on a certain direction? I have to project on it. Okay. And then whatever is left over is left over. So this is also part of the definition is that the projection of the leftover stuff is 0. And what is this stuff? Right? See along the null space now. So this is where the beauty of this calculation comes in. Remember the definition is 0 to R, right? C. Sorry, 0 to 1. I'm scaled now, right? So this is just going to give me half. But this is nothing but the cross-section average. I'll call it right? Just like I defined the velocity cross-section average, I have the concentration cross-section average. So the beautiful thing about this is this mathematical decomposition ends up being very physical, right? Because I'm writing the concentration field as the cross-section average plus deviations, where the deviations are such that their cross-section average is 0. Right? So you get the average part here, and all fluctuations about the average is sitting here, and those fluctuations will average out to 0, right, by definition. Okay? And already you can see that if there is rapid diffusion in R, you can expect that its effect will be to take you to the average and smear out this C tilde. So somehow it makes sense that if this is the direction along which things are proceeding slowly, right? And this is the fast variables, the diffusion will make this stuff vanish. Right? So this split makes sense physically. Of course, this is just a projection, it's a scalar. I need to multiply it by a vector because this is a vector, right? So that vector just is 1. That's why it's not there. So this is a function, right? This is just a number. So when I project, I should project it on the function multiplied by the normalized function, right? The function here is just 1. That's why so I don't have to write it there. Let it be there if you want. And then this C tilde is a function. So in other words, I'm saying that I have C bar, okay? Oh, sorry. Cross-section average. This will be a function of what now? Not R anymore because I average it out. Only X and T. So you see the projected stuff onto the slow manifold now will evolve slowly in time and only depend on the other slow direction. It no longer depends on the fast direction, which is R. Okay? But the deviations will depend in general, right? Will depend on R. They will also depend on X and time. But because I'm going to look for a solution on the slow manifold, right, that dependence will be slaved to this. That is the key point. Otherwise, there is no point in what I have done. Right? So it will depend implicitly on X and time through C. Right? Or if you want me to I'll just put it like this. So that is what we saw in the last X and Y. Remember, we said Y is varying in time, but once you hit the slow manifold, its time dependence is through X. So Y will be a function of X, but because X is changing, Y will change. That's the meaning of being quasi-static, right, in the more accurate way. Okay, so there will be variations. I have to calculate what those variations are as a function of r, but the amplitude of the variations will vary in time only through their dependence on c bar. So I'm not saying variations are 0, that is important. Okay, because if I make c tilde 0, I'll also get some approximation, some ad hoc approximation. What will I get? Suppose I put c tilde 0, that's like saying c is equal to just c bar. Right? If I do that here, right, and I say, okay, c is just c bar, right, then this will pop out, right, it will drop out, and then I will get some, I mean, it will drop out from there. We'll see in a second, okay, but that's, I think, I'll show it to you in a second in a better way. Okay, but the crucial thing is we're not saying it is 0. It is some non-zero thing. It's just that its time and space evolution in X is going to be happening through C average. Okay, that's because I'm on the slow manifold. Now, if I don't care about slow manifolds, I just do that perturbation technique which I'm showing you now, called Lyapunov-Schmidt. I would realize, okay, that kernel of L is non-zero. I cannot determine C naught, so I abandon that approach. I come here and I project C onto that kernel, and I have the deviations. I will not make this assumption here right now, but you will see that when I do the calculation, it will automatically happen because I'm doing a perturbation calculation. In other words, if P is small, in general, C tilde can be anything. But if P is small and I calculate the concentration evolution for P being small, this will happen automatically. But that is basically why I can say I am justified by looking at the slow manifold, because automatically I will be on the slow manifold when P is small, right? This is the logic. Okay. Fine. So this is my decomposition, and I again have the fact that this integral is 0, right? So the average of the C tilde must go to 0. That's what I know. And the boundary conditions on C tilde will also follow the same as C, right? Because this doesn't have R dependence. So I know from here that, so I have 3 conditions on C tilde. Right, so that is my full decomposition. So that was step 1, right? I decompose, so it's like choosing the right coordinate system, right? I have a field C, which is infinite dimensional, right? So I can write it as a sum of many different functions. Here it's only a 2 split, right, where I'm projecting it on the null space, and then I have everything else. Now I have to do the second thing, which is to project my governing equation, to split that, right? And remember, when I'm working in C, I'm working in the domain space of the operator. So I'll project it onto the null space and the complement. Right? That's the function of the space of functions on which L is acting. But now when I come to the equation itself is a function, right? That lies in the domain space of L. Sorry, in the range space of L, right? It's what comes out after you operate L on it, right? So that's on the domain. But because I have a one-dimensional null space here, I will have the range space will not span the entire space. It will have a complement. That means some part, a one-dimensional part, which is not part of the range. So I have to project it onto that. Right? Onto the complement of the range of that same operator. Okay, and what's important is that the range complement of the operator is equal to the null space of the adjoint operator. Let me use a dagger. So if it was a matrix, I would say the transpose of the matrix. And so in general, I have to determine what this adjoint is. Only then I can project. Okay. We'll see what that is in a second, right? But so as not to break the flow of the derivation, I will just tell you for now that in this problem, L is equal to L adjoint. That is, L is self-adjoint. Okay, we'll see how to prove this later. Right, and it will play an important role in the next lectures. But let's take it for the moment. All that means is that if I want to project the equation suitably, I need to just project it onto 1 again. Right? If it was not self-adjoint, the vector that spanned this range complement would not be 1, it would be something else. And I have to project onto that something else. Okay, that means I do the integral with respect to that something else. But now that's not the case, right? I can just, it's just 1. Okay, that means 1 spans not only the null space of L, it also spans the range complement. So that means when I project it onto the range complement, I'll get a one-dimensional equation. That's what I want, right? I want a reduced equation. I start with an infinite dimensional PDE, I will get a one-dimensional in the sense in the R direction, which I am reducing. Okay. So let's do that. So what does this mean? It just means you take my equation, multiply by 1, integrate. So there's a factor 2, right? That factor will cancel, so I'm not worried about it. Right? R dr. Right? So I'll have R dr, and then I have rho c by dou t, correct? Plus u rho c by dou x on one side, and then on the other side again the same thing, into okay, this is projecting it onto 1, because 1 is the vector that spans the range complement. But it's nothing but taking the cross-section average of the equation. So again, once again, because you have this nice interpretation, the split in the domain space was project the concentration field into its cross-section average plus deviations, and then you take the original equation and average that also. Right? You just take the cross-section average of the equation. Sorry, correct. Thank you. 0 to 1, right. So I'm doing cross-section average of the equation. So because in this problem the kernel vector is very simple, it's just 1. So what we do with this advanced technique ends up being the same as some naive averaging. So if I want to say, okay, let's get an equation for cross-section average, I will write C as cross-section average plus some error, if you like, or some deviation. Okay? That is this. And I will define the deviations to have 0 average. This is kind of obvious. I could do it on physical grounds. Right? And then I say, okay, how to get an equation for C bar for a cross-section average, right? How to get an equation for how this evolves. The only equation I know is a full PD, so let me go and average that. Right? This is a kind of obvious thing to do. So in the initial phases of this exercise of model reduction, this is what people did, just intuitively. Okay? And it would work for some problems and it would fail for other problems. And it was not clear what was happening. Right? So that's when this theory was developed, and with the basis of that we can see, okay, in some cases it will work precisely in those cases where your operator had a null space and that null space was something simple like 1, then it would be the cross-section average. But you can imagine some other problem where you have a null space, but the null space is not 1, it's some function. Right? So for example, it could be like some function of R, right, which is not uniform. Then I will still do this, but the appropriate average now is not the usual cross-section average, it is some average with respect to some weight function, which is actually that null space, you see. So it's a special kind of average. And it is only that special kind of average which will give you a good model. So this is the idea behind weighted residual. So weighted residual is nothing but integral with respect to a weight. Okay, so there's a whole plethora of techniques around these things, and then that's how these things emerge. Okay, in many cases they were developed sort of intuitively. So if this cross section doesn't work, someone will try some weight function and it will work. Okay, but now we have a good systematic way of understanding what's going on. Okay, anyway, so in this problem it's simple, right? You can just do this. So let's see what happens now. So because, in fact, this is nothing but LC. Right, so what is this? This is simply, right? But I already know, right, that LC will be in the range. I mean, by definition, this gives me a vector which lies in the range of L. And I'm projecting it onto the range complement. It should be 0. Right? Because the outcome of this, so if you want, I have some space, right? There is a range complement here and the range is the floor. So LC will put something into the floor and I'm now projecting it onto the vertical area. Of course, it's going to be 0, right? by definition. So this is just to check that, right? But if I've done things correctly, this has to be 0. So that is the beauty of projecting it onto the range complement. By doing this, you knock off the leading operator and you automatically get all the small terms balancing each other, which is what you want. Okay, so let's do this now, this calculation. This is just this, right? So if we do it, R and R will cancel. You do one integration, right? I'll get R dou C by dou R evaluated at 1 and 0, which are 0 because of my boundary conditions, right? So this is of course 0. But that's guaranteed because of what I am doing. I'm projecting LC onto the complement of its range. It's going to be 0. Okay, so now what's more interesting is this stuff. So the R direction has gone off basically. By averaging, I have removed the R direction. That's not magic, it's happened by construction, right? Because the R direction is surviving in my equation because of the operator L. And by projecting LC onto its range complement, I'll knock it off. So in other words, this is the right coordinate along which to project the equation so that I get rid of all the fast variables, I get rid of the R direction. Right? So I only have now x and time left. But I have to do this thing. So you'll see now that I can take the time out of the first term, right? So I'll get ddt of just the cross-section average. Right? I can, of course, I have multiplied it by 2 on both sides. So then I have ddt. And now here, I can't do that, right? Because this u depends on R. That is important. If u didn't depend on R, then it would just come out. But here u does depend on R. And you can write it in the following form. Right, where this Cm okay, and this Cm is, does anybody know what this is? It's also a nice physical average, which people had introduced on purely physical grounds before. What is this? It's called the cup mixing average. Okay, so the idea is, suppose I stand at a distance, this is of course a function of x, right? So I stand at some x distance in the pipe and cut it, and then hold a cup and collect some fluid for some time, stir the cup and check the concentration. Right? That would be like saying, okay, let me take all the volume that leaves the reactor in some time and then look at the mean concentration there. Okay? But that's just this, right? Because I'm multiplying C by the U. So UC is like the flux, the flow rate of material. So it's like taking the total flow rate of material dividing by the area. So actually I should be more careful. Then it makes sense. Otherwise, it's not a concentration error. So I've taken the total mass of the species divided by the flow rate of the fluid. But you see, what is this? This is nothing but the mean concentration, okay, which is scaled in my problem to 1. Correct? That's why it will not appear in my calculation. This is nothing but U average, but because I scaled U by U average, this denominator becomes 1, right, in my scale problem. So in my scale problem, I'll just get this. Okay? So now this is my equation. So it will be nice to write it, let me write it like this. No, actually it's okay. Okay, but this is just 1. Half, where? No, so I mean, I had 2 on both sides, right? Otherwise, this also should have that 2 and 2, and doesn't matter. Okay, so we have reached a point now where we have some kind of one-dimensional advection equation, right? Because remember, we threw away diffusion in x because it was r square by L. So in x direction, all that remained was advection. You would of course have time. So we have some kind of pure advection equation. The catch is that you don't have C average here, you have this cup mixing average. So I need to know what is the cup mixing average in terms of C bar. That's just another fancy way of saying I need to know C tilde. Because over here, I still have this integral. That's the integral I had here. I really need to replace C by C average plus C tilde. That C tilde doesn't play a role in this term because I would take the integral of C tilde becomes 0. So C tilde only survives here. Why? Because it gets multiplied by U. So U times C tilde integral is what I need to close the equation. So in other words, I have to find C tilde. I'll just reformulate it in a way that's physically more intuitive because you have the time evolution cross-section average depends on the advection of this cup mixing average. In chemical engineering literature, these two kinds of averages are popular for various reasons. Okay, but it's the same as saying, okay, here I have an unclosed term that depends on C average and C tilde. And I need to find C tilde as a function of C average. That is the determination of the slow manifold. If I know that, I can plug it in this equation and I'll get my closed equation. Okay. So at this stage, it looks like I have only advection, but this will not account for the spreading of the pulse, right? If this Cm was C bar, if this Cm was the same as this cross-section average, if I give a pulse, it will just stay the same size, so it won't diffuse in the x direction. So clearly this has to be different from that. That means C tilde has to be not 0, because if I put C tilde 0, this C will be same as C cross-section average. It won't depend on R. I'll pull it out. And U average will cancel. So I'll get here C average. So you can see now that if I make the naive assumption that C tilde is 0, the diffusion causes everything directly to become just uniform. The diffusion completely uniformizes the R direction. If I say that, I'll get just pure advection. This will not account for the Taylor-Aris dispersion, which always exists. Right? So the fact, no matter how small, the fact that there is this finite radial direction, right, gives you a effect because you are waiting for infinite time. So no matter how small the difference of time scale is, you are waiting for an infinite time. And that build-up gives you some difference, and that difference is what's going to account for this spread. Right? If you say, no, I have very fast radial mixing, so I'll just assume that the concentration is uniform, is equal to cross-section average, you'll get completely qualitatively long result. Right? So this is another example of a singular perturbation problem, which is in fact why you could not determine a solution for C naught. So singular perturbation is whenever you have a small parameter, you try to take the limit, and then you get a result that doesn't smoothly match what you have when P is actually 0. Right? So if P were actually 0, I would get C is actually uniform and then this answer. But for any finite P, no matter how small, you will be qualitatively different because you will have this Taylor-Aris dispersion effect, right, if you wait for long times. Okay, so, and that's already signaled by the fact that when you try to do naive perturbation, you couldn't determine the solution. And because you have a 0 eigenvalue of that operator. So many different ways of looking at it. Okay, so the main thing is that center manifold is powerful because it doesn't make this assumption, right? It actually calculates the fast variables, it gives them definite values, but it calculates them in terms of the slow variables. It doesn't just put them to 0. Okay, whereas in typical, especially in the earlier years, the engineering kind of ad hoc approach was just to put the fast variables to 0. Sometimes it works, sometimes it fails miserably. Right? And now we know how to do it properly, right? Which is to do this slow manifold type construction. Okay, so then that will give us the correct answer. Fine. So we are now in a position where we have this equation. I need to now find Cm or C tilde equivalently as a function of the cross-section average. Right? For this will bring me to step 3, which we will carry on in the next lecture. And this will be to look at, so I need an equation for C tilde, basically, right? I've got my equation for C cross-section average. Where will the C tilde equation come? Of course, from the original PD, the stuff I have left over, right? So that will be like, project now my equation onto the range. Right? So I project range complement. I have to take the leftover. Okay? So to do this projection, of course, this projection is easy. Right? So I just take my original equation and subtract that out. That will obviously give me the leftover stuff. And the key thing is that this activity, taking the equation, subtracting out the projection onto the range, that is precisely what is needed to satisfy the solvability condition on the operator L. So because L has a null space, you know its range will not span the entire space. So I cannot take any arbitrary right-hand side and invert L. Right? If the right-hand side of, for example, this operator L something equal to right-hand side, the right-hand side cannot be arbitrary because the right-hand side lies in the range complement. I cannot invert because nothing that L acts on will ever give me that vector in the range complement. Right? So I have to remove out from the right-hand side the stuff that is in the range complement. That's exactly what I did here because I projected out the equation that projected out, this is the RHS now, right? That projected out the RHS onto the range complement. This is the stuff that lies in the range complement. I'll have to take this, multiply by 1 and subtract out of my original equation. Now I will get a corrected right-hand side which I can actually solve. And that solving that will give me C tilde. Okay, so we'll do the activity in the next class, but this is what I was saying also previously, right? That even if I don't do this decomposition, I directly try to solve the equation, you will encounter this problem. You will get L C tilde equal to some RHS. To get an equation correction for C tilde, to solve for C tilde, I'll have to put the RHS into the range. That will force me to do this activity. And that will give me the equation for C cross-section average. Okay, so different ways of approaching the same thing, but the underlying idea is the same. Okay. Fine. So in the next class, we'll do this calculation and see how it gives us this dispersion.